Today, we're starting off with some fun with fractions. For this first thing that I'm going to do, I really wouldn't even bother taking notes. This is just, I'm going way back in time to talk about multiplying fractions. And then we will fast forward to talk about multiplying rational functions. That's the part where you should be taking notes. Once upon a time, we talked about multiplying fractions. I don't even know if this is how you saw multiplication of fractions. It doesn't really matter. I just want to talk a lot. I want to kind of take this back to previous conversations about what the denominators mean on these fractions. So when I see these, I think of the top number as telling me how many of something we have, and the denominator as telling me the size of the something. When we go to multiply fractions, like 2/3 times 3/4, what this is really saying is if I took one whole thing and I took 2/3 of it, that means I'm going to cut it into thirds in this direction. And I'm going to take 2 of them. And then in the other direction, I've got 3/4. So again, the denominator tells me the size of the thing. So I'm going to cut this into fourths. And I'm going to take 3 of them. Then thinking about multiplication is really finding area. I'm saying that we need the 2/3 in this direction and the 3/4 in the other direction. So all told, the number of things that I end up with is 6. I end up with 6 of those boxes. And then the denominator is the size. Well, because I cut it into 3 pieces this way and 4 pieces this way, the size of each box is a 1/12. There are 12 boxes. So I've got 6 of the 12. And with the heart of it, when we're multiplying fractions, this is like the underlying thing that's happening. But functionally, we're not drawing out boxes. If I see 2/3 times 3/4, I have 2 options. I either think about multiplying straight across. So 2 times 3 gives me that 6. 3 times 4 gives me the 12. Or I could think about rearranging the terms. Because they're all multiplication here, I could regroup things and kind of group that 3/3 together and recognize that, hey, 3/3, that's an invisible 1. And then get down to 2/4, and I can think about 2/4 and either break the 4 apart to be a 2/2, a 2 times 2, so that I get a 2/2 that's equal to 1, and eventually get to this 1/2. It doesn't matter what way you simplify yourself through the fractions when we're talking about numbers, but really the point that I wanted to get across is that when we're multiplying fractions, we're multiplying straight across the top to come up with the how many of the thing, and we multiply straight across the bottom to come up with what's the size of those things. If we can multiply fractions, let's just do one more quick multiplication problem with fractions where I'm not drawing it out. So if I had 3/4 times 10/21, I could multiply these straight across and say 3 times 10, that's 30, 4 times 21, that's 84. And then somehow try to reduce that to lowest terms. That's never what I would actually do. I don't want to make numbers bigger if I could make them smaller instead. So if I was actually presented with this problem, what I personally would do is to look at that 10 and really see that 10 as 5 times 2. And in the denominator, see the 4 as 2 times 2. And that 21 as 3 times 7. Because it's all multiplication, now I can group the things to find my invisible ones. 3 over 3, that's a 1. And 2 over 2 is also a 1. And I know I made this really messy now, but I'm down to a 5 on the top and a 2 times 7 on the bottom, or 5/14. I don't care at all whether you show work on this problem or not, but what would be important is recognizing that we can get this down to lowest terms. And if we can do it with numbers, then we can do it with polynomials also, where that first step is to think about factoring things out so that we can find those invisible ones to cancel out for us. Well, if we can multiply fractions, we can also divide them. Again, this is just a refresher with numbers, and then we'll get on to the polynomial stuff. 3/5 divided by 15/7. For starters, we honestly almost never write this symbol in calculus, just being real. What we would actually write here would be something like 3/5 giant division bar divided by 15/7. But this takes up way more space on the page. So I think textbooks tend to write it like this, even though we'd almost never write it like this in real life. Okay. Probably some of you remember that when you divide, you flip and multiply, or some other little catchy phrase. I just want to back up for a second to make sure that I never want you to just like take my word for it or take some other teacher's word for it. Back to basics. Math is always built on some small foundational principle, and then we work forward from that. So going back to, I think I used the same example yesterday, but 6 divided by 3 is equal to 2 because 2 times 3 is equal to 6. And if I took that 6 divided by 3 and I rewrote it using this division symbol, that would look like 6 divided by 3 is equal to 2 because 2 times 3 is equal to 6. If I write out that same because statement for our current problem, then the because statement that goes with this would look like, if I'm kind of matching where things are, that 2 was the piece on the side. So I'm going to have, oh, I need a piece on the side because I needed an equal sign. Give me a second. This is equal to, I don't know. If I went out to write that same because statement, this would look like the piece I don't know times the 15/17 is equal to 3/5. Well, if I'm trying to get this question mark piece by itself, it is true that I could divide by 15/7, or I could think about the other way to move this to the other side of this equation would be to take that 15/7 and multiply by 7/15. And as long as I did that on both sides of the equation, I wouldn't have changed the problem. Why the 7/15 over here? So that my 7s cancel out to give me that 1, and the 15/15 cancel out to give me the 1. So the shortcut for how to get to this final answer is to reframe the original question to actually say 3/5 times 7/15 is equal to what? This is a place where kind of trying to stay neat with your handwriting and keeping things on a nice straight parallel line is sometimes helpful, or my personal favorite, write big. I make fewer mistakes on the whiteboard, and I'm convinced that's because I'm just writing bigger. So my first thing here, if I'm going to multiply or divide, is not to distribute everything out. I'm going to do the same thing that I would if I had numbers, and I'm going to try to factor and cancel things first. So looking at this, x minus 2 and x plus 3, there's nothing to simplify there. And I can't factor anything, but x squared minus 1, that's the difference of squares. This can definitely be factored. And on the 2x minus 4, I can factor out a 2. I'm looking at x minus 2, x plus 3. That will just keep those pieces the same. Because it's multiplication, I can make this one big bar because we're multiplying straight across the top, straight across the bottom. So that x squared minus 1 rather, it's going to factor as x minus 1 times x plus 1. And the 2x minus 4, I can factor a 2 out. And that would leave me left with an x and minus 2. And I'm just going to step back, see if anything cancels out for us. The x minus 2 over x minus 2. That's going to give me a 1. And now, here's the thing. Don't go back and multiply things out again. Honestly, just leave them the way they are. Leave it in its factored form. X minus 1, x plus 1, x plus 3 times 2. Very first thing I'm doing, if I've got that division symbol, I'm going to rewrite this. So I'm looking at 9 over, I need 2 steps at once. I might as well factor a 2 out here because I can already see that there's a 2 that I can pull out. Save myself from writing it another time. Over here, I'm going to have a minus 4 over 3. I can already see that those a minus 4s are going to give me a big fat 1. And I could just multiply straight across on the bottom, but 9 divided by 3, I can also simplify. And 9 divided by 3 is going to leave me with a 3. And then I've got that 2 in the denominator. Of everything up here, that a squared minus 25, that's what I want to be jumping out at you. Difference of squares. That kind of factoring shows up so often. It was showing up in your trig homework for Math C. It shows up everywhere. So that's probably what jumps out at me first in terms of factoring. Over here, this is also kind of a special factor in the sense that this one happens to be a perfect square. So if I need to get a squared, I know I need a and a. And there's actually only one way I can get 25. That's 5 times 5. So we kind of hope it works. And it will, because as long as I have 5a plus another 5a, that would give me my 10a. Now I'm just going to be careful about canceling out factors. My a minus 5 over a minus 5, that's going to be a 1. A plus 5 over a plus 5, that's another 1. And a plus 5 over another a plus 5, well, dang, the whole thing is equal to 1. Good times. If I start with this piece up here, it's not a trinomial and I have something cubed. So really I'm hoping, is there anything I can pull out of the terms? And I can pull a y squared out of both of those terms. When I do that, I'm left with a y minus 5. In the denominator, looks like I can also pull a y squared out of all the terms. And when I pull a y squared out, I'll be left with y squared plus 3y plus 2. So now I better check that and see if that factors even more. Well, to get that y squared, I would be hoping for a y and a y. There's actually only one way to multiply two things and get 2, and that's with a 2 and a 1. That's positive, so they have to have the same sign, and looks like that's going to work. Because when I distribute it back out, I'll have a y plus a 2y and get that 3y. I'm going to replace the factor. I'm going to replace this piece of it with its factored version. This is another place in terms of time saving. I mentioned that if it's got a division symbol, just go ahead and write multiplication and flip it. If you look at this problem and you can already see that you're about to factor out the y squareds, why not write it the first time around with that y squared factored out? Again, it's just all about, can we shave a little bit of time off of these problems to get a little bit more efficient with the algebra piece, so we've got more thinking time for the parts that are a little more complicated. And that thinking time is going to be more and more important as we move through calculus. Looking over here, y squared minus 2y minus 3. Well, to get that y squared, I need a y and a y. There's only one way to multiply and get 3 and 1. And if I use a 3y and a y, I can definitely get a negative 2y as long as the 3 is negative. In my denominator, I've got a couple of ways that we can multiply to get that 6. A 6 and 1 or a 2 and 3. Now it turns out I can make a 5 with a 6 and a 1 or a 2 and a 3. So it is important that I look at the sign here. Because it's positive, because I'm getting a positive 6, I know the two factors have to have the same sign. So thinking about the 6 and a 1, that's not going to work, because if they have the same sign, that's going to give me a 7 or a negative 7. So the 2 and the 3 are what I need. And they're both going to need to be negative because it's a negative 5. Once I've got the factoring part done, then I'm just looking for factors that are going to give me a 1. So y squared over y squared, there's a 1. Y minus 3 over y minus 3. Y plus 1 over y plus 1. And after I do all that stuff, the factors that I'm left with in the numerator, I've got a y minus 5. And in the denominator, I've got y plus 2 times y minus 2. And I think that's going to be my final answer. Okay, back to doing some math. More factoring. Good times. So this next example, there's x's and y's both in the mix, but that's okay. We shouldn't let extra variables scare us. I'm just going to start one piece at a time. So if I look at this piece up here, I've got 2x squared plus 4x, and I'm thinking, is there anything I can pull out of those terms? Looks like I can pull out a 2x. And if I pull out a 2x, then from the 2x squared, I'd have an x left. And from 4x, I'd have a 2. Now, when I say pull out, I really just mean that I'm factoring it so that if I were to distribute it back in, I would get what we started with. Pull out isn't really a mathy term. It's really factoring. So when I look at the bottom, I have the difference of perfect squares. I've got an x squared and a y squared. So even though that y squared is not a number, we're still going to factor it the same way. It's going to look like x minus y times x plus y. Now comes the fun part. I used to really fight factoring by grouping, but the truth is that when it's just sitting there for you, it's really nice. So when I look at the numerator here, I've got x's and y's mixed up together. It's not a trinomial. I have more than 3 terms. I'm really hoping to factor by grouping. So I'm going to take the pieces in the order that they're in and hope that that works. So when I look at my first group, the thing that they have in common is an x. And if I pull the x out, actually, let me do it up here just to save a little space on the board. So here I can pull an x out and then I'd be left with an x plus 3. And from my second group, I can pull a y out. When I do that, I'm left with another x plus 3. So now that I've grouped them, now I can factor them. Now each of these has an x plus 3 in common. So the x plus 3 I can pull out in front, and then I'm left with that x and that plus y. In my denominator, we almost did exactly the same factoring. I know we need an x and an x. I know the signs have to be the same because that's positive. And I know they both have to be positive because they're going to add up to be 5. So this time it's going to have to be a positive 2 and a positive 3. Then I'll just quickly go through and cancel out anything that I can. Let's see, x plus 3 over x plus 3. I've got an x plus y and an x plus y. I'm not going to try to make my giant 1 reach over there. I'll do the more conventional thing and just run a line through them. X plus 2 and x plus 2. And looks like when all is said and done, I'm left with a 2x on the top and an x minus y on the bottom. 36 inches, and I wanted to convert that to feet. My guess is that a lot of you could just do that in your head, but if I were doing this in a mathy way, I always think about, where am I starting? Well, I'm starting with 36 inches. I want to end up with feet. So my ratio that I write down needs to have what I want on the top. So I'm going to put feet on the top. And I know that I'm going to have to cancel out those inches. So I'm going to need inches on the bottom. And now I'm just looking for, what is the ratio of feet to inches? Well, there are 12 inches to 1 foot. My inch units are going to cancel out, and that's going to be 36 over 12 feet, but I want to make sure to reduce that to lowest terms. You can probably do 36 divided by 12 in your head and get the 3. If not, you can always break these up into smaller pieces. So that 36, I might think of as 6 times 6. And then if I think of 12 as 6 times 2, then I can get rid of that. And then 6 divided by 2, you can probably get to 3 in your head. If we do another quick conversion here, and I take 4,000 seconds, and I want to convert that into hours. Again, I'm starting with 4,000 seconds. I want to end up with hours, so I'm going to put what I want on the top. I need my seconds to cancel out, so I'm going to put that on the bottom. And then I just need to know, what is the ratio? Well, the ratio is 1 hour to 60 seconds. So my seconds cancel out, and I could write this as 4,000 divided by 60 hours. But we want to reduce that as much as we possibly can. So for starters, I can definitely divide the top and the bottom both by 10, or the other way to think about that is to rewrite that 4,000 over 60 as saying 400 times 10 over 6 times 10, so that my 10s will cancel. And then if I do a little bit more factoring, I can factor the 6 for sure into a 3 times 2. And I can factor the 400 into a 200 times 2 and make the 2's go away. And then 200 divided by 3 that's probably where I would leave it. You should not be afraid of the words. So I don't want to write out the entire problem for number 10, but this is that fuel consumption problem. So what we're told is, and I'm kind of just going to pick out the numbers part. And we're told that it travels 168 miles on 3.5 gallons of gas. And what we've been asked is to give the fuel consumption in miles per gallon. And there's a note on there. The computer just wants the number. The units are going to be miles per gallon, but the computer just wants this as a number. Well, if I need miles per gallon, that statement of per means that whatever comes right after the per is what goes in the denominator. So I need this to be miles on top and gallons on the bottom. Gallons, not gels, gallons on the bottom. So I've got 168 miles over 3.5 gallons. Honestly, you could quit there, but I would either, at this point, pick up a calculator or, I'd pick up a calculator. Let's be real. I mean, I want to know how many miles I get per gallon. I don't know what 168 divided by 3.5 is. I'm going to pick up a calculator and go, 168 divided by 3.5. Dude, that car gets some good gas mileage. 168 divided by 3.5, man, that's 48 miles per gallon. That's like crazy good gas mileage. That's like, I don't know, 1990s turbo diesel Jetta kind of gas mileage.